both the SPM and IGCSE physics syllabus. There's always a lot more to know about the users. So if you'd like to find out more, please feel free to do your own research or watch my other educational videos. What I'll be covering in this video is the general information that you would need to be able to answer the questions in your examinations. So what we will be covering in this video are smoke alarms, food irradiation, sterilization, measuring and controlling thickness as well as levels, water pipe leakage detection, medical imaging and tumor detection, as well as radiotherapy. So a lot of students always think, radioactive radiation, isn't that only used in nuclear power plant? That is one of the uses, but there's a whole lot more. So we're not going through nuclear power plants in this video because there is another lesson which we will go through nuclear power plants in more detail. For this lesson, we'll focus on the daily possible uses of radioactive radiation. Now, before we go into the uses, first of all, we need to be aware of how suitable radioisotopes could be chosen for an application. There are two things that we need to consider. For one, you need to consider the type of radiation. That means, do we use alpha, beta, or gamma? Now, this is very important because it depends on how we're going to use this radioactive radiation. Alpha, beta, and gamma have their own unique properties. For example, because of their nature, they have different ionizing powers, they have different penetrative powers. So depending on their characteristics and their properties, we have to consider those when we want to choose the suitable radioisotope. Another thing that we must consider is the half-life. Half-life, if you recall, is the time taken for the radioactive radiation to decrease its mass or activity, which is the count rate, by half. If you can't remember alpha, beta, gamma radiation, or if you haven't learned it, please watch my video on nuclear emission. And as for half-life, please watch my video on half-life. For now, we're going to go into the uses. Let's start with the smoke alarm. Now, some smoke alarms do have radioactive material in there. So if you find a smoke alarm has that radioactive label there, yes, there is radioactive material in there. But if you're wondering, oh my God, isn't that dangerous? How can they put radioactive material in a place where there's general public? That's the thing. We have to consider the type of radioisotope that we want to use. Usually, the radioactive material here is an alpha source. Normally, it's americium 241, which is an alpha source. The gray color bit here is the container. Normally, this is how we would draw the container holding the radioactive material. And it's placed like this because we want to prevent the radiation from escaping this side so that the radiation only comes out this side. Now, why do we use an alpha source? Because alpha has the greatest ionizing power. So what happens here is when americium-241 releases alpha particles, the alpha particles will ionize the air particles over here. So the air particles, which I'm going to draw in green, will become ions, positive and negative. So here's the smoke alarm. These are two electrodes or two electrical plates that are part of a circuit, and you can see that they're not connected. So these plates, positive plate and negative plate, it's an incomplete circuit. The purpose of alpha particles here is to ionize the air particles, and these air particles will complete the circuit. So the negative charges will go to the positive plate, positive charges will go to the negative plate, and that completes the circuit. Now let's say this is the buzzer. So when the circuit is complete, the current will flow this way. It won't flow through the buzzer because normally they hook it up in such a way that the buzzer will have very high resistance. So what happens is the current will flow this way, will not flow through the buzzer, so the buzzer does not make a sound. So again, the alpha source will ionize the air particles to complete the circuit. So let me write that down. alpha particles ionize the air particles, which will complete the circuit. So, how does it detect smoke? Because when smoke enters, let's say these yellow particles now are the smoke particles, the smoke particles will be attracted to the ions. And when they get attracted, they will stop the ions from moving to the electrical plates, therefore preventing the ions from completing the circuit. So when the circuit is no longer complete, what happens is then current will flow through the buzzer and the buzzer will make a sound. And that's how the smoke alarm works. So when smoke enters the smoke alarm, the smoke particles prevent the ions from completing the circuit. So why is it safe to use a radioactive material in general public? Because if you recall the nature of alpha particles, alpha, for one, doesn't travel very far. It only travels a few centimeters in air and also is easily stopped. So something as thin as a piece of paper can already stop alpha from traveling. So you'll find that the smoke alarm, normally there is a lid and a container. It just has holes to allow the smoke particles to come in, but otherwise it will prevent the alpha particles from being released. And that's why even though smoke alarms may contain radioactive material, they are safe to be placed in general public. Plus, smoke alarms are always placed on the ceiling because smoke travels up. So because it's on the ceiling, it's not easy for people to climb up and try to open the smoke alarm or for naughty children to try to pry it open. Okay, so these are all the considerations that have already been taken into account when building the smoke alarm. So in this case, we are using an alpha source. And in terms of the half-life, because we don't want to have to change the radioactive material so often, we use something which has a long half-life. For example, americium-241 has a half-life of 470 years. The longer the half-life, the longer it'll be radioactive. So you don't have to keep changing and swapping and replacing the radioactive material. Next, food irradiation. This process also uses radioactive radiation. So what happens here is we will shine gamma rays through the food. And why we use gamma is because it can go through the tin, and because of its extremely high energy, it's able to kill microorganisms easily. Now, what happens inside the can is if there were any bacteria, microorganisms trapped inside the cans, because gamma is able to penetrate the tin, it will kill those microorganisms. And because the cans are sealed, no new microorganisms can come in, therefore keeping the food fresher for longer. Remember, what makes the food decay is the presence of bacteria that will cause the food to spoil. So by getting rid of those bacteria and those microorganisms, the food can stay fresh for much, much longer. Besides irradiating cans and boxes, we can also irradiate things like fruits. So similarly, by irradiating the fruits with gamma radiation, the gamma radiation would kill any microorganisms like spores, bacteria, fungi inside the fruit, keeping the fruit fresher for longer as well. So when the microorganisms have been killed, we don't have the bacteria and microorganisms that could cause the food to decay and spoil, allowing the fruits to stay fresher for longer, especially during import when it travels from one country to another. For this, we need to use gamma because gamma's high energy is able to penetrate and kill microorganisms. We also want to use something that has a long half-life because the source over here, which is irradiating the gamma, we don't want to have to change this gamma source often, just like the americium-241. So when this has a long half-life, we are able to use this particular radioactive material for much longer, and we don't have to keep replacing the radioactive material. This also applies for sterilization. So let's say, for example, we want to sterilize the hospital equipment that is used for surgery, like all these utensils. It's very important when doctors do surgery on patients that they don't introduce new microorganisms where there weren't any present. So, what they normally do in hospitals is they put all the surgical tools in a sealed container, which then they place into a special machine known as an autoclave, which will release gamma radiation that can penetrate the packaging to kill all the microorganisms that's on the surgical tools. And just like with the tin cans, because this is sealed, no new microorganisms can come in. And that's how we're able to sterilize the surgical tools effectively. So again, we also want a gamma source that has a long half-life so that we don't have to keep replacing the radioactive material that is the gamma source over here. Another use is to measure and control thickness. So what is this? So for example, if let's say we want to make sheets of paper or sheets of metal like aluminium. So normally in production, they'll have rollers that will basically press out those sheets, which you get the sheet material. And to detect the thickness, instead of having someone there with a micrometer screw gauge to measure the thickness, we can automatically detect and control the thickness using radioactive radiation. So how that works is we have a radioactive source on one side, and the source will shoot a radiation that's through the material and detected by a detector on the other side, which is connected to a sensor, which can then change the pressure when needed. So now think, if this is too thin, will there be more or less radiation that can pass through? More, right? So when it's too thin, you get a high reading. So when the reading is too high, what happens is it will send a message to the rollers to decrease the pressure so it'll become thicker. But if it's too thick, what happens? Yes, lower reading. So when the reading becomes a bit too low, then what happens is the sensor will then inform the rollers to increase the pressure so that it becomes thinner. So this is automatic, and normally there's a certain range. You can't have a specific number, oh, it must be this number. There's a specific range that is acceptable for the thickness. So if it's outside this range, the rollers will adjust the pressure accordingly. Now, the type of radiation is very important as well. We can't use alpha because alpha can't even penetrate a thin piece of paper. So no matter how much alpha you use, it won't be able to penetrate. If you use gamma, gamma is extremely penetrative. So no matter whether it's thick or thin, you're going to get the same reading on the other side anyway. So that's why this is normally a beta source, because beta has a penetrative power that lies between alpha and gamma. So when it's too thin or too thick, beta can show a difference in the reading. Again, we want a long half-life so that we don't have to keep changing the material that's inside the radioactive source. We can also use the same concept to measure and control the levels of liquids inside a container. So for example, over here we have the source that will shine the radiation at different levels. And on the other end, we have a series of detectors. So normally we place detectors at different levels in order to get the reading. So just like with the thickness, if there is nothing blocking it, you'll get a high reading. And if there's liquid in the way, the reading will become low. So by determining which level has the low reading and which level has the high reading, we can approximate the level of the liquid that's inside a closed container. If there's any adjustments that need to be made, then this can be done automatically based on the readings that are obtained. So just like with thickness, we want to use beta and of course a long half-life. Now, we can also use radioactive radiation to detect underground water pipe leakage. How does that work? You see, the thing is, if water was leaking somewhere along the way during the transport of water, if we have no idea where the leakage is, we wouldn't know where to get started, right? You can't be randomly digging up areas. Ooh, I think it's here. Oh, it's not there. Sorry. Ooh, wrong area. Sorry. So you do need to at least pinpoint or at least approximate the rough area where you know the leakage is. So how this works is, now, normally, we would place a radioactive source inside the water at the source. That means where the tank is. And the kind of radioactive material in this case has to be something that can dissolve easily in the water and chemically is safe. Normally, we would use radioactive salt. Salt is normally sodium chloride. So the sodium ion in this case is normally the radioactive material. So we normally use sodium 24. That means the sodium chloride salt, the sodium ion is radioactive salt. So that means in sodium chloride, the sodium ion is a radioactive sodium. So what happens is when we add the radioactive salt, this radioactive salt will then be transported along the water pipe. That means now the entire water is radioactive. Now, if this area is where the leakage is, that means there's a lot of water that's gathering here. That's also where a lot of the radioactive salt would be. So, to determine the area where there's a leakage, what we'll do is we'll walk along the surface here with the Geiger counter or the Geiger-Müller tube, and we try to find the area where there's a reading. So, obviously, because the water is radioactive, you'll get a reading throughout the entire pipeline. But where the water has gathered, that's where the radioactive salt is also concentrated at. That's where you'll get a higher reading because there's more of the salt there. So if the entire area you find this is where the highest reading is, that's where the water pipe leakage is likely to be. That's how we detect the water pipe leakage. Now, because we need the radioactive material to be able to penetrate the ground, the penetration ability of the radioactive material must be high enough. Alpha and beta are not that penetrative, so they're not suitable. That's why we have to use a gamma source. Now, also, this is water that human beings are going to drink and also going to be used by animals and plants. Obviously, we don't want this radioactive water to kill us. So, we need to use something that has a short half-life. So, although the water is radioactive, but if something has a short half-life, it means that its radioactivity level will decrease very quickly. So, for example, sodium 24 has a half-life of 15 hours, long enough for us to be able to detect, short enough that the radioactivity level will drop to a low level that's safe after a few days. So that's why we can use sodium 24 safely, even though it's radioactive, because its half life is short enough that it won't keep the water radioactive for a very long time. And in terms of medical imaging and tumor detection, it is similar to the water pipe leakage. So, how it works is this. Let's say we want to examine the circulation system of a patient. So, what they will normally do is they will inject a radioactive tracer into the patient. So, radioactive tracer means a chemical that has some radioactivity. So, for example, if we want to examine the circulation system, we can inject radioactive iron because blood cells need iron. It will absorb that radioactive iron and transport it throughout the entire patient's body. So inject it in. What happens is the iron would then spread out through the entire patient's circulation system. And then we have the patient go through a detector and then we detect, okay, what's the overall reading of the iron? So in this case, the imaging system will show the radioactive iron that's throughout the patient's body and able to show how the patient's circulation system is like. The tumor detection is also similar because tumors are extremely active. They will tend to absorb more of a particular nutrient. So if you inject that radioactive nutrient into the patient's body, the tumor will absorb most of it. And when we do the imaging, you'll find that a particular area has high radioactive levels. That's where a tumor could possibly be. So in terms of using radioactive tracers like these, we cannot use alpha because alpha cannot even penetrate human skin. So typically we will use a beta or a gamma source so that at least we can see how the distribution is throughout a patient's body. And because we are injecting the radioactive tracer into the patient's body, the patient will become radioactive. So obviously, we don't want the radioactivity level to remain high in the patient's body. So is it okay to use radioactive material? Yes, as long as it has a short half-life. Long enough for us to run an imaging scan, short enough that after a few days, the radioactivity level will drop to a safe level so that the patient is no longer radioactive. So for radiotherapy, we would normally use gamma radiation because gamma radiation has an energy level that's high enough to kill living cells. So we focus the gamma radiation onto the tumor to kill the cell. For this, we definitely need a gamma source because alpha beta not strong enough to kill the cell. So gamma and a long half-life because again, we don't want to keep changing the radioactive source inside the machine so that we can use this machine for a very long time without having to replace the radioactive material. So in general, remember that if the radioactive source is outside the patient or outside the food source or outside the animal or plant, we use something with a long half-life. But if it's going to be injected or consumed, we use something with a short half-life. There's a lot more uses of radioactive radiation, so please feel free to do your own research. But for now, this is the end of this lesson. So if you found this video educational and helpful, please click like. And of course, subscribe for more lessons, solutions, and exam strategies from your physics teacher, Miss Ho. Happy studying!